Ladies and gentlemen, class recording has started. So, yesterday we introduced the concept of atomic mass. What does the atomic mass describe for us? Hannah, go ahead.
Is it the comparison to carbon-12?
Okay, the atomic mass of an atom is a comparison of that atom to carbon-12. Carbon-12 is the standard that we use to compare all other atoms. And we went through that already, okay? And so, what value do we give to carbon-12 in order to use it to compare to all the other atoms? 12. We say that the carbon-12 atom has a value of 12 AMUs, which are atomic mass units, and those are our standards of comparison, okay? But later on in the class period, we introduced the concept of average atomic mass. What does the average atomic mass tell us about? Atomic mass and average atomic mass are two different things. Atomic mass compares an atom to carbon-12. What does average atomic mass tell us? What does it take into account for us? Okay. What does average atomic mass describe for us? Well, go ahead. The size of the atom, but what else does it tell us about? Or what else is important? Not just the size of atoms, but what else? Okay, that's atomic mass, right? But when we were going through these examples here, not only did we need to know how big an atom was in relation to carbon-12, what else do we need to know? How often each one of those isotopes shows up, right? So these pictures here, on the left, we had an even number of 81s and 79s, right? Okay. And that meant that the average is right in the middle. But on the one on the right, we had more 35s than 37s, and so the average was closer to 35. Right at the end of class yesterday, I gave you this slide that shows us how we take into account what the atomic mass of each individual atom is, but then also how often that atom shows up, okay? And so here we do this calculation for all of the isotopes of that element, and once we do that calculation for all the isotopes, we add the individual calculations to give us the average atomic mass, okay? Conceptually, are we okay? Does that make sense? Okay? All right. The sheet that I gave you today, up at the top, it says average atomic mass calculations, okay? Let's go through number 1 together, just so we've done an example of this, and then we can move on to the stuff for today. All right, so it says, naturally occurring copper consists of 2 isotopes. Based on the information listed below, calculate the average atomic mass of copper. First, what are isotopes? That'd be good. Say again. What are isotopes? No, what are isotopes in general? Same number of protons, different number of neutrons, right? So here we have copper 63 and copper 65. You don't have to do this now, but you should be able to tell me how many protons, neutrons, and electrons copper 63 has, how many protons, neutrons, and electrons copper 65 has. Okay, because there are 2 isotopes of copper, we have to do this calculation twice, okay? So let's start off. Let's do it first for copper 63. So going back to, here, let me do this so we have it reference-wise. Okay, here.
What's that noise?
So it just took a little picture, right? So,
Wow.
all right, so now it's here down at the bottom. Okay, so we don't have to keep flipping back and forth. All right, so the first calculation, it says we take its atomic mass. This column here gives us the atomic mass, right? So for copper 63, we're going to do 62.93, okay? And then we're going to multiply it by this fraction that says abundance over 100. The abundance is just the percentage. So we look on the chart, what percentage is copper 63? 69.1. Okay? And then we put that over 100. Okay? We run this through your calculator and come up with a value for this calculation. Or if we say here, this contribution. Okay? And go ahead. That's what that fraction is doing, basically, right? It's turning your percentage into a decimal. Okay? So I will say this, and any shortcuts that make sense to you mathematically to reduce the number of steps that you can do, feel free to do that, right? If you're getting the right answer, that's fine. I don't care if it saves you some calculator strokes or whatever. That's fine too. Yeah, if you understand that basically putting that number over 100 is just moving the decimal place over 2 places, fine. Do that. Make it fast for yourself, and that's okay. All right. So when you plug this in here, what do you get as far as the contribution of copper 63? Zach, what do you got? 43.484. Okay, 43.484, right? Okay. Here, I'm going to cut it off at that spot right there, okay? Because, and somebody asked about this earlier, so it would probably be good to bring this up. Technically here, if we're doing sig digs, right? This is 3 significant digits, but this isn't a measurement, okay? It's just like a number that we have, okay? So, and this is going to be true when we go forward here. Let's make our significant digits just match the number that we started with. So this has 4 significant digits, so I'm going to have this one be 4 significant digits over on the side over there. In fact, you said it was 43.484, right? Okay, so we don't have to round that 8. We'll just cut it off at that spot, okay? All right, this is how much copper 63 contributes to the average. But because we have 2 isotopes, we have to do this calculation again for our second isotope. So copper 65 has an atomic mass of 64.93, but it only shows up 30.9% of the time. And so we do this calculation now for copper 65. And what do we end up with? 20.06? You good with that? All right. We have done these 2 isotopes individually. We have figured out their individual contributions. Okay? What's the last step here? Add them together. Okay? Do not add them and divide by 2. We're not taking the average of these contributions. Doing this fraction right here takes into account that one shows up more than the other one. So all we have to do here is add. We'll go here, we'll go here, and we end up with this. Okay? Because this is an atomic mass or an average atomic mass, it's a comparison. Right? We use AMUs as the comparison. Now, that's not a measurement, right? You can't get a ruler that has AMUs on it. That's not what AMUs are. AMU is just a way of us comparing it. What are we comparing it to again? Carbon 12. All right, did we get the right answer? How do we know? Where could we go to check if we got the right answer?
The average.
Go to the periodic table, right? Find copper on your periodic table.
Oh my gosh.
And what did we get?
The same thing
Pretty close. We got some rounding issues and stuff like that, but you know, for the most part, we're pretty good. That's copper's atomic number, right? You know, we want the average atomic mass, we want that other number on there. Yeah, that's a good question. If your rounding was off just a little bit on the test, that'd be fine. You know, like, yeah. I would be worried if you got like 62.7, like that would be a problem. But if you got like 63.55, like that's fine. Okay. All right, are we good here? Okay. So next part, like I said at the beginning of class, I would expect a lot of you to be able to do these calculations without going through the steps that I would like us to take. But again, I'm not getting the right answer, and getting the right answer as fast as possible is not the main objective today. It's setting up a system that we can use to attack any kind of problem from this point forward, because we will do this quite a bit moving forward, okay? So here, we're going to start looking at this page here that says Honors Physical Science Problem Set, Conversion Factors up at the top. These are actually some screenshots of the book that we used to use for this class. I like how they describe things a little bit better than your book does. The process is the same, it's just not from your book because it's from a different book, okay? All right. In the top left-hand corner, you have a worked out example. So you don't necessarily have to write anything down right now, but I want to use it as a template of what we're going to do, okay? So it says, what is the mass of exactly 50 gumballs? First, whenever we're attacking any problem, what's the first thing we should do? What's the first step of the scientific method? Ask a question. That's the first step we need to do here. What's the question we're trying to answer here? What is the mass, right? So here, our question, right? The answer, if it says what is the mass, we're trying to find out how many grams does 50 gumballs weigh. Okay? That's the question we're trying to answer. And that's what we should really go through in each problem that we do. What's the question asking us for? What is this thing that we're looking for? Because it's hard to make a plan if we don't know what we're trying to get to. Okay? Once we've asked a question, the next step in the scientific method is to do what? We ask our testable question, right? Make a hypothesis. But what does our hypothesis have to be based on?
The question.
No. Well, yes, it should answer the question, but what do we base our hypothesis on?
Our knowledge. What we think is the answer.
Yes. Our knowledge is
Our knowledge of past events.
which we call, what do we call those past events?
Past events.
Heard of that. Future.
F?
Facts.
Facts is what I said.
That's what I said.
Laws and
Theories.
Right?
Wow.
Okay.
First try.
Hypothesis. Well done, everybody. Well done. So, remember when we talked about facts, laws, and theories, it was like 95 degrees outside? Yeah, not anymore. So, anyway. All right. Facts, laws, and theories. That applies here too. Facts, laws, and theories are things that we know. In this problem, they gave us the mass of 10 gumballs. Now, I really think that most of you could probably figure out, if I know the mass of 10 gumballs, to get the mass of 50 gumballs, what should you probably do? Multiply by 5, okay? I know that you can do that. But let's use this information, again, to set up a process to go through when the answer isn't that obvious. Okay? Let's go ahead. Say, well, here, we'll go through and do this. Okay. All right. This unit, or this exercise today, is going to introduce us to something that we call a conversion factor. Okay? A conversion factor changes the unit of a value but doesn't change the actual value. Okay? It changes how we represent a value, but not what that value necessarily is. Okay? For example, here we're trying to find out the mass of 50 gumballs. Okay? So we know at the end of the day we're going to have 50 gumballs. But we don't want to know how many gumballs we have. We want to know how much mass they have. So we have to go through the process of turning a count of 50 gumballs into a mass. Okay? That's our goal in this problem. All right? So, we have started off, down here at the bottom, okay, you can see that they have started off with writing 50 gumballs. Then they multiplied this 50 gumballs by a fraction. This fraction is the conversion factor that we're using in this problem. Okay? Notice 21.4 grams, 10 gumballs. Up here, the yellow section, they gave us that 10 gumballs equals 21.4 grams. What's true about the top of this, or the numerator of this fraction and the denominator of that fraction? What separates 10 gumballs and 21.4 grams in the yellow highlighted section? An equal sign. What does that mean? They're equal. All right? 10 gumballs and 21.4 grams are equal to each other. Now, if we put two things that are equal to each other in the numerator and the denominator of a fraction, what is that fraction equal to? 1. If we multiply something by 1, what do we get?
The correct 50.
Itself. Remember that we said we're not changing the actual value, we're just changing how we represent it. We're not changing the number of gumballs that are in this problem, we're just representing it as a mass. Okay? Now, why this way? Well, we're multiplying. Okay? If it makes your life easier, you can put 50 gumballs just over 1, not 1 gram or 1 meter or 1 second, just the number 1. Okay? I just took a whole number and turned it into a fraction. Right? Now we are multiplying two fractions together. Okay? What procedure do we use when multiplying two fractions together? What do? Multiply the numerators, multiply the denominators, right? Okay, now, here's the reducing part, right? This is the this is the reason why it's set up this way, okay? Here, 10 gumballs and 21.4 grams, we learned up here, right, are equal to each other. So whether the 21.4 grams is in the numerator and the 10 gumballs is in the denominator, or vice versa, that's basically the same fraction. But by setting it up this way, putting gumballs here in the denominator, we have a gumballs in the numerator and a gumballs in the denominator. If you have one thing in the top of a fraction and the other thing in the bottom of a fraction, what will they do to each other? They just cancel each other out, right? So by setting up our conversion factor this way, gumballs went away here and gumballs went away here. Just the units, not the number. The 50 is still there, but the gumball is gone. Okay? Which is important because what is the unit that we want on our final answer? The grams. No, not the G of the gumball. We want the grams. If we go back to this multiplication problem that we're doing down here, what's the only unit that's left now in any one of those fractions? Grams, and that's what we want, right? So now we can multiply across the tops, we can multiply across the bottom, and we end up with 107 grams. Okay? Good there for starters. Let's go through some examples, okay? All right. Building on the problem that we just did. These are the problems that show up like on your sheet, okay? So this is like directly underneath where it says practice conversion factors number 1. What is the mass of exactly 150 gumballs? Again, I know that a lot of you could probably do the problem just like this, but let's go through the process, okay? The question says, what is the mass? So what unit should our final answer have? Grams, right? So we want to know how many grams we're talking about here, okay? What information or what amount did they give us to start with here? 150 gumballs, okay? So we're going to start with 150 gumballs. All right. Conversion factors get rid of bad units and give us good units, or get rid of units that we don't want and leave us with units that we do want. So, if you would like, go ahead and put gumballs over, or 150 gumballs just over 1. So now we have a fraction, okay? But then we're going to multiply it by a conversion factor. A conversion factor is a fraction. So, this is the information that they gave us. This is what we want to get rid of. In order to do that, I'm going to write a times sign, and I'm going to write a fraction bar. Times sign, fraction bar. That's like the first of 100,000 times you'll hear me say that. They're probably not that many, but a lot. Okay. All right. This fraction right here is going to be our conversion factor. When we are setting up conversion factors, my suggestion to you is to work with units first. Okay? What unit should we put in the bottom of this conversion factor? What unit? Gumballs. We're trying to get rid of gumballs in this original number. In order to get rid of gumballs, the unit that is in the top of the first fraction, we should put gumballs, not gunballs, in the bottom of that conversion factor. Conversion factors get rid of bad units and leave us with good units. What's the good unit that we're looking for here? Grams. So this conversion factor should have gumballs as the unit on the bottom, and it should have grams on the unit as the unit on the top. Start with the units. What are we trying to get rid of? What are we trying to be left with? Okay? Now, what did we say has to be true about the top of this fraction and the bottom of this fraction? They should be equal to each other. They should be the same, right? This information still applies. So now we're going to put numbers in to make the top and the bottom of this fraction equal to each other. 21.4 is going to go in front of grams. 10 is going to go in front of gumballs. Good? Okay. Now let's do some math. Okay? Audrey. Gumballs top, gumballs bottom. What's going to happen? They're going to cancel each other out, right? So that unit and that unit are going to go away. What's the only unit now left in our entire problem? Grams. That's good because that's what we're trying to find, right? So now we do some multiplication. Here we multiply 150, not 150 gumballs because the gumballs is gone. Just 150 times 21.4 grams. Okay? Then on the bottom, 1 times 10. Not 10 gumballs because that gumballs unit is gone, right? Just 1 times 10. All right? So plug that into your calculator and let's get a number here. Okay? Shouldn't be 21. Oh, 321. Okay. It shouldn't be 21. Heidi, go ahead. No. So, because that's part of the quiz on Friday. You're going to have to do one of these on the quiz, right? So,
Do I have to write gumball?
yeah. You have to write what?
Gumballs, like the
Yeah.
gumballs.
Yes. No. So, the reason why you can, like in your head, you know to do that because you understand that relationship between gumballs and grams, right? And you understand that 150-ish is just 15 times 10, blah, 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 right? We're going to come across some problems later on this week where those relationships are not going to be like just as easy to see. And so regardless of whether you know the relationship or not, we can go through this process of setting up the conversion factor, putting units where we're supposed to put them, and that will give us a plan to get where we need to get to. Okay? That's why I wanted to start us with this. Even though I know you could just take that and multiply it by 15 and get what you need to get, but when you come across a relationship that you don't understand as well, you're not going to know what to do because you don't see it as clearly as you do this one. Okay? All right, so last thing. 321, are we good with that? Okay? All right, so let's round this the way we're supposed to. Conversion factors. Conversion factors don't have significant digits. They are exact numbers. So when we are rounding final answers significant digits wise, we go to what we started with. How many significant digits are there in 150 gumballs? So that zero, good. That zero is not significant because there's no decimal point. Okay, so just the two significant digits here. 321 as written is how many significant digits?
3.
That's 3, right? All right, so we start at the beginning. Is 3 significant?
Yeah.
Yes, so we're going to keep the 3. Is 2 significant?
Yes.
Yep, we're going to keep the 2, but that's our 2 significant digits. Is our answer 32 though?
No.
No, right? 32 is a lot different than 321. What do we do with this 1 right here?
Replace it.
That becomes that 0. I don't know if I'd eat it or not, but you know, so, okay. All right, so 320, is there a decimal point at the end of this though? No, because that would turn it into 3, right? So that would round to 320 grams. Okay? All right, good there? All right, let's do one more real quick before the end of the period. Okay? So, question number 2 here says, if you want 50 eggs, how many dozens must you buy? How many extra eggs do you have to take? Let's take the first question. What is this question asking us for?
How many dozens?
How many dozens, right? Okay. So here, how many dozens? Okay. Easy, everyone. Easy. I know what time it is. Don't worry. Okay. All right. So, how many dozens? Okay. What information did they give us to work with?
You have 50 eggs.
We have 50 eggs. So 50 eggs is going to be what we're trying to get rid of. Okay? Now, if you would like, you can just put that over 1 and turn it into a fraction. Now we set up our conversion factor. Conversion factors get rid of bad units, leave us with good units. Time sign, fraction bar. Start with units. What unit should go on the bottom of this conversion factor?
12.
What unit
Eggs.
should go on the bottom? Eggs on the bottom, right? And then what unit should go on the top of that conversion factor? Dozens should go on the top. Now we said, what has to be true about the top of a conversion factor and the bottom of a conversion factor? They have to be equal. What numbers do we put in here to make the top and the bottom equal? 1 dozen, 12 eggs. Okay? What's going to happen to eggs in this problem?
Get canceled out.
Eggs is going to go away, right? The only unit we're left with now is what? Dozens, and that's good because that's what this asked us for, right? So now we do some multiplication, right? We multiply the tops, we multiply the bottoms, and I think it's 4.16.
4.16 and
Okay. Okay. So 50 eggs is a little over 4 dozen eggs. Okay? Does that make sense? Now, to answer this question, right? how many dozen of eggs would you have to buy? If you you'd have to buy 5 dozen eggs, right? Because this 50 eggs is a little over 4 dozen. So you'd have to buy 5 dozen eggs, right? How many extra eggs would you be left with?
Let me just do that math right there. Then.
You'd be left with 10 extra eggs. All right. Okay. Yes, Drew.
Kareem says you can't buy eggs in a 6-pack. In fact, I've seen.
Oh, you definitely can buy eggs in a 6-pack.
Yeah.
Not all places sell eggs in a 6-pack, but some places
What
do.
if you got like 18 packs of eggs?
Oh, you can get 18 packs too. So.
Does that make it easier? That makes it a lot.
All right. Tomorrow we'll do a couple more conversion factor problems, and then we'll get into doing conversion factors with atoms. Okay? Hey, last reminder: if you haven't turned in or if you haven't finished up your Bean Lab yet, please make sure that gets taken care of and turned in ASAP.
If that's it,